Building a computer network requires integrating hardware from competing vendors, multiple types of physical cables, and complex software formats into a single, unified system. Early attempts at this integration resulted in what engineers called chaos networking. Addressing, data syntax, and signal loss lacked any standardized rules. If a machine sent data, there was no guaranteed structural method for the receiving machine to understand the transmission, resulting in complete failure. This diagram illustrates the framework adopted to organize that complexity. Left is chaos networking. Right is the OSI model, ISO standard 7498-1. It uses strict abstraction decoupling, separating the process into 7 layers. Lower layers handle physical hardware. Upper layers manage software data. By decoupling these tasks, discrete engineering domains like cable manufacturing and web app development can function independently. This allows engineers to update physical hardware or cabling standards without needing to rewrite the logic of the applications running above them. The absolute base of the network is Layer 1, the physical layer. This is the domain of mechanical specifications and raw electrical bit streams. The actual transmission mediums operate here, including Category 5E twisted pair cabling in local networks, or fiber optic lines running through a vertical backbone. Basic network hardware operates strictly at this physical level. A network hub takes an incoming electrical signal and pushes it to all connected ports. A continuous stream of raw ones and zeros lacks local organization. Layer 1 has no mechanism to target delivery to a specific device. Layer 2, the data link layer, provides localized order, packaging raw bit streams into structured blocks called frames. This layer introduces MAC addressing. A MAC address is a hard-coded identifier embedded in a network interface card, providing a physical target for the frame. Hardware switches operate at Layer 2 by reading these MAC addresses. Unlike a hub, a switch filters and forwards frames directly to their intended physical destination, which eliminates collisions on the network segment. Without Layer 2's specific hardware addressing, physical cables would be instantly overwhelmed by colliding traffic, rendering local data transfer impossible. MAC addresses work for localized delivery, but cannot route traffic outside of their immediate network segment. Layer 3, the network layer, solves this barrier using logical addressing. This is where the Internet Protocol, or IP, is applied to the data packet. Routers function entirely at Layer 3. They connect disparate networks by reading these logical IP addresses. To calculate the optimal pathway across a global network, routers communicate using specialized routing protocols, such as OSPF or RIP. When moving a large packet onto a network with a strict size limit, a router utilizes fragmentation, dividing the packet into smaller pieces. Intervening routers do not put these pieces back together. Reassembly only happens at the final destination system's Layer 3. By applying logical addresses, Layer 3 abstracts away the variations in physical hardware. It lets packets traverse the globe regardless of the underlying cabling or switches they pass through. Layer 3 routes packets to the correct host machine, but offers zero guarantee that packets will arrive intact or in the correct sequence. Layer 4, the transport layer, handles data segmentation and flow control. The Transmission Control Protocol, TCP, ensures reliable transmission by returning an acknowledgement signal before shipping the next packet. Alternatively, the User Datagram Protocol, UDP, provides connectionless, best-effort transmission without error checking. If data arrives faster than the receiving system can process it, Layer 4's flow control actively throttles the transmission rate to prevent memory overruns. Layer 4 acts as the bridge between hardware and software. It takes the variable delivery of lower layers and stabilizes it into a reliable stream. Moving into the purely software-driven upper stack, Layer 5, the session layer, establishes virtual circuits and synchronizes the ongoing data flow between the two endpoints. But even when raw data arrives safely and in sequence at the host machine, it is often structurally unreadable by the final destination application. Layer 6, the presentation layer, is the network syntax translator, where network engineering meets software engineering. It handles character code translation, ensuring that an incoming EBCDC coded text file is converted into a standard ASCII file for the receiving system. It resolves structural differences in string representation,
whether the program uses C++ or Pascal formatting. A vital function here is serialization, collapsing complex, multi-dimensional data objects into flat, standard byte strings like JSON or XML. Data encryption and decryption for security purposes also predominantly execute at this presentation level. Finally, Layer 7, the application layer, provides the end-user interface. It delivers network services, like HTTP or email, directly into the user's software. Layer 6 acts as the structural glue of the software stack. It allows software engineers to pull data from APIs without ever concerning themselves with the specific formatting of the underlying data transmission. The OSI model provides the universal diagnostic vocabulary for networks. In practical application, modern networks operate on the simplified TCP/IP protocol suite. This chart condenses OSI's 7 layers into TCP/IP's 4. Layers 1 and 2 combine into the network access layer. Layer 3 maps to the internet layer. Layer 4 translates to host-to-host. Finally, layers 5, 6, and 7 group into a unified process layer. In TCP/IP, the process layer handles tasks like JSON serialization and HTTP interfacing simultaneously, without dividing them into separate discrete steps. Understanding this dual structure allows engineers to quickly isolate issues. They can immediately define whether an error is an IP fragmentation failure at the internet layer or a syntax serialization bug at the process layer. Ultimately, the OSI model provides a conceptual map for the communication process. Mastering this decoupling allows an engineer to categorize specific failures within a network and apply the precise protocol required to resolve them.